So the last part we really talk about in thermodynamics is thermal conductivity. Entropy is not really that big. It's very conceptually answered. So we'll just talk about thermal conductivity. There's only one key equation. You might have learned more entropy in your chemistry classes and such. But for thermal conductivity, we're talking about heat flow. We're talking about the rate at which heat flows through an object. Okay, so Q is the amount of heat. So in this case, what are we talking about is, let's say you have like heat's flowing through the wall, like it's cold outside, like there's a temperature difference, right? So it's cold out here, it's hot here, and we're talking about like how does the heat tends to go from hot to cold, how does the heat flow through an object? Or maybe you might have a metal rod, right? And there's two different temperatures, like one side is hot, T1 and T2, and you know the temperature at T2 is greater than T1. Again, how does the heat flow from, and how quickly does it flow through the object? Some objects conduct heat very quickly, some do very slowly. So what we're looking at here is what is the rate at which heat flows? Delta little t is the time. So the ratio of the heat to time is like how quickly the heat is flowing through here. And it's based off of four factors here. K, which is the thermal conductivity. This is a constant. The thermal conductivity is the faster heat flows through it. It's based on the physical characteristics of the object. So metal has a different thermal conductivity than say wood, than say air, things like that. A is the cross-sectional area. Delta big T is the difference in the temperature between the endpoints, and L is the length. So the bigger the area, the more heat flows, which kind of makes sense. Like if I have like a thin rod, then not that much heat's going to flow, but I have something big, like a big area, then more heat's going to flow. The longer it is, like the thicker it is, think about it like a thick blanket, the slower heat will flow. Right? And then the bigger the change in temperature, the quicker heat will flow, right? Because that means it's like big. That's why, like, you know, if it's really cold outside, your house gets colder very quickly because there's a bigger temperature difference. Okay, second law of thermodynamics simply says that is about entropy. This is the last, like I said, this is conceptual. This is all you really need to know. Entropy is the amount of disorder in a system. And in a closed system, entropy can only increase. In other words, let me give you an example in terms of like gases. Like this, like let's say we have gas particles here. All right, they're all through in here in a room. In a case like this, let's say all the gas particles just happen to be like all in a corner like this. This is a state of low entropy. Low entropy meaning like everything is ordered very well because all of the gas is located in one spot. Whereas this is more random, more spread out. This is high entropy. So the more disorder in your system is, the funny joke is kind of like your room's probably, I don't know, maybe you're very clean, but your room's probably very messy. My room's very messy. And that's, the messier it is, the more entropy there is. And this statement is that the entropy only increases. That means another way to think of it is like your room will, on its own, without active effort on your part, your room is just going to get messier and messier and messier over time. Okay, so it's just going to increase over time. So you can argue with your mom that the room is only getting messier because of second law of thermodynamics, that the entropy has to increase. Okay, so let's take a look at an example here for the thermal conductivity. So we have a rectangular iron rod with a thermal conductivity of this K, has dimensions shown with labeled A, B, and C. Let's see. Okay, yeah. And then if side C is placed against a heat source of 300K, the opposite side C is placed against a heat source. So they're putting this side is 300K, and this side is 200K. How much heat would flow through the rod in 1 minute? So let's look at our equation here, like this. Is equal to Ka delta T over L. Now, what do we know? We want to know how much heat flows in 1 minute. So that's going to be Q over 60 seconds. K is 80.2. The cross-sectional area would be this area here. It's going to be 0.5 times 0.1, and it's all in meters still. What's the difference in the temperature? 300 minus 200. And then what's the length? The length here from this side to this side is going to be 1.5. Okay, so that's going to give you 80.2 times 0.5 times 0.1 times 100 divided by 1.5. That gives you 267.3. That's over 60, so we got to multiply by 60. 60 times that. And I get 16,040 joules. Okay. If side A is placed against it, so now that we're putting it around here, how much is the rate of heat flow change compared to the heat flow in part A? So let's look at this. So it's Q over, how does the rate of heat flow, how does this part change? So Q over delta T is going to be 80.2. What's the area of side A is going to be 1.5 times 1. And then the temperature difference is the same. But now the length is only 0.5, right? So if we look at this and compared to this number here, 80.2 times 1.5 times 100 divided by 0.5. This is 24,060. Okay, and that is a lot bigger. Let's just see how that compares. Oh, where did I get the 0.1? This should be a 1.0. Sorry, I messed this up. So this would be times 10. Sorry. I don't know where I got the 0.1. So it'd be like this. So how much more is it? 2460 divided by 2673. 24,060 divided by 2673 is like 9 times more. 9 times more. Okay. All right. A house uses insulation to reduce heat flow out. If you want to reduce the heat flow by a factor of 2, how can you change the following aspects of the insulation? So the heat flow is this part. The thickness of the insulation. Well, if I want to make this by half, I got to double it, right? So the thickness is the length. It's like how thick we make that wall. So it'd be times 2. Thermal conductivity, if I want it half, I want it times 1/2. Because if I multiply the K by 1/2, then this thing gets multiplied by 1/2. I want this quantity to be multiplied by 1/2. Explain why it would be difficult to change the cross-sectional area of the insulation. Well, it's a wall, right? That would change. That can't change the size of the house. Of the wall. Right? So that's that. Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.